At the core of a district cooling system are its main components: chillers, pumps, cooling towers, thermal energy storage, and an advanced control system that keeps everything running efficiently. In this session, I'll be focusing on thermal energy storage technology. Thermal energy storage, TES, is an important part of modern cooling systems, particularly deployed in district cooling systems. It helps store cooling energy when demand is low and then release it when demand is high. By doing this, TES makes cooling systems more efficient, reduces the need for extra equipment, and lowers costs. For example, cooling energy can be stored at night when electricity demand is low, so-called charging, and later the charged energy is used during the day when more cooling is needed, namely discharging. Essentially, the TES helps shift energy use from busy periods to quieter ones, improving efficiency, lowering operation costs, and supporting sustainability. These advantages make DCS an increasingly attractive solution for industries and communities. Thermal energy can be stored in different ways, each with its own advantages and trade-offs. The two main types of commercially available storage systems are sensible storage in the form of chilled water tanks and latent storage in the form of ice tanks. With chilled water storage, water is cooled to about 4 degrees to 5 degrees. This method is called sensible thermal energy storage. It is relatively efficient because the chiller only needs to lower the temperature slightly, which reduces energy use for chiller operations. By contrast, ice storage, a form of latent thermal energy storage, requires the chiller to cool water to around -3 degrees C to -5 degrees C in order to produce ice. This deeper cooling makes the system less efficient and more energy intensive compared to producing chilled water at 5 degrees C. The trade-off, however, is that ice storage has a much higher energy density. For the same tank size, ice can store about 3 times more energy than chilled water. In summary, chilled water storage offer more energy-efficient operations, but lower storage capacity. Ice storage offers much higher storage capacity, but less efficient operations. In addition, a newer technology called phase change material, PCM, thermal energy storage is being developed. While still in the research and development stage, it has the potential to combine efficiency with high storage density. Let's discuss about water storage tank. Water storage tanks, often called water TES, are widely used in district cooling systems. These tanks can be built either horizontally or vertically. Horizontal tanks are laid out flat and used where there is more ground space, but they tend to have weaker thermal layering, which makes them less efficient. Vertical tanks, on the other hand, provide better energy storage performance, take up less space, and are the preferred option in most large-scale cooling systems. Therefore, this article focuses on the operation of vertical water TES. The operation of a vertical water TES is straightforward. During charging, the chiller produces more cooling energy than the customer demand, and excess chilled water from the chiller is pumped into the bottom of the tank, gradually replacing the warmer water until the entire tank is filled with cold water. When cooling demand rises, the tank discharges by supplying chilled water from the bottom while warm water enters from the top. Over time, the tank shifts between fully charged, when it is filled with cold water, and fully discharged, when only warm water remains. This is the operations of a vertical water TES tank. Another important type of TS is latent energy storage, often implemented as ice storage. A common design is the ice ball system. In this system, small balls filled with water are placed inside a tank containing a brine solution. During the charging phase, the brine is cooled to below freezing, which causes the water inside the balls to turn into ice. Later, during discharging, the brine absorbs cooling from the ice and passes through a heat exchanger to chill water for the cooling system. The use of a heat exchanger is necessary because brine cannot be supplied directly to customers due to its corrosive nature. There are several types of ice storage systems available in the market, each designed to meet different needs. Another ice storage technology is the ice-on-coil system, which uses a heat exchanger specifically developed for thermal energy storage. In this system, a brine solution cooled to around -5 degrees C circulates inside copper tubes. During the charging process, the cold brine removes heat from the surrounding water, gradually freezing it into ice around the tubes. During discharging, warmer brine flows through the tubes and absorbs cooling energy from the surrounding ice, delivering it to the system. In practical applications, the selection of a thermal energy storage technology depends on several factors, including available space, investment and operating costs, system complexity, and the project's specific requirements. A strong understanding of the different TES technologies, combined with operational expertise, is essential for making the right choice.